Here's a definition of a complex conjugate. If we let z equal a complex number a plus bi, then z with a bar above it is called the conjugate, z conjugate. So this bar right here means conjugate. And if we want to know what the conjugate of z is, the real part is going to keep its value. However, the imaginary part will change its sign. It's that simple. So let's practice a couple. Determine the conjugate of each. We have 3 plus 2i, negative 8 plus 5i, 6 minus I, and negative 4 minus 3i. The conjugate of 3 plus 2i is 3 minus 2i. The real part keeps its value. The imaginary part changes its sign. The conjugate of negative 8 plus 5i, the real part keeps its value. The imaginary part changes its sign. 6 minus I, the real part keeps its value. The conjugate changes the sign of the imaginary part. Negative 4 minus 3i, its conjugate keeps the real part while changing the sign of the imaginary part. Now, what's interesting in each of these cases, just like what happened on the previous page when we multiplied a number and its conjugate, we multiplied, what did we multiply? We multiplied 7 plus 2i times 7 minus 2i. So I'm just going to write that over here. We multiplied 7 plus 2i times 7 minus 2i, and we computed just a value that was a real number, no imaginary part. We're going to try to do the same here for each of these. We're going to take this number and we're going to multiply by the conjugate. 3 plus 2i times 3 minus 2i. The first values would be 3 times 3. The outer is negative 6i. The inner is positive 6i. Those cancel out. Negative 6i plus 6i cancel out. Positive 2i times negative 2i is negative 4i squared. That becomes 9 plus 4, which is 13. No imaginary part. Negative 8 plus 5i times negative 8 minus 5i. Negative 8 times negative 8 is 64. Negative 8 times negative 5i is positive 40i. 5i times negative 8 is negative 40i. 5i times negative 5i is negative 25i squared, which becomes 64 plus 25, which equals 89. 6 minus I times 6 plus I. 6 times 6 is 36. That's our first. Our outer and our inner are going to cancel out. Outer is 6i, inner is negative 6i. Our last is negative I times positive I, which is negative I squared. There's a 1 as a coefficient. The I squared changes that negative 1 to be a positive 1. So we get 36 plus 1 is 37. Our last pair of conjugates we're going to multiply together. Negative 4i minus 3i times negative 4 plus 3i. Negative 4 times negative 4 is positive 16. The outer is negative 12i. The inner is positive 12i. And the last is negative 9i squared. That becomes 16 plus 9, which is 25. So what I want you to take a really close look at is the fact that in every single circumstance we're adding two positive numbers together. That's the first thing. The second is we're taking the a value and multiplying it by itself. So 3 squared is 9. And we're taking the b value, which is the coefficient of I, and multiplying it by itself, giving us 4. 2 times 2 is 4. Let's try that again. Negative 8 squared is 64. 5 times 5 is 25. Notice how we were always adding the two numbers together. 6 squared is 36. 1, that's a 1. Let me put a 1 there for you. That's a 1. 1 squared is 1. Negative 4 squared is 16. And negative 3 squared, I'm so sorry, just 3 squared. You don't even have to look at the negative. But even if you did negative 3 squared, you're always going to end up with a positive. So even if you do that, even if you take that sign and associate it with that coefficient, you're absolutely fine, because if you square it and multiply it by itself, you're still going to end up with a positive number. So when you take an imaginary number, a complex number, and multiply by its conjugate, you will always be adding two positive numbers together.